Okay, we are on section 19.4, motion of a charged particle in a magnetic field. Let's share the PowerPoint. Now, a few things we need to get straight, and that's these little green X's. So if you think of an arrow, just the type of an arrow you shoot with a bow and arrow, it's got a point on one side, and if you were to look at that point, it would look like a dot. And then there's the back side. You have the little feathers. I think it's called the fletching on the back of the arrow. And so you would, if this were an arrow, you would be looking at the fletching, the little feathers on the back of the uh, uh, arrow, and that's what you're looking at basically here. These little green X's are the backs of the arrow. So this tells you that the magnetic field is going into the screen here. So it's going away from you. The magnetic field is going away from you, and we've got a charged particle, a positive charged particle with a particular velocity. We'll start looking at the one on the far right, the one that's going directly vertical. Let's do a right-hand rule on it. We've got the magnetic field going into the screen. We've got the velocity going straight up. It's a positive particle. Palm means positive, remember? And so the force is towards the center, and so that makes it curve. And once it gets to the top, there's the magnetic field, there's the velocity, here's the force downward. Well, what do we have here? We have a centripetal force. We have a centripetal force. This centripetal force is going to keep this positive particle going around in a circle. So we see that we know that the force is equal to QVB sine theta. Well, we said at the beginning that this particle, maybe I didn't say it, but we'll say it now. This is a particle that's directed perpendicular to the magnetic field. Well, if it's perpendicular, then the theta is equal to 90. Sine of theta is equal to 1. So it's just QVB. The force is equal to QVB. But wait a minute, if this is a centripetal acceleration, we also know that force equals mass times acceleration. The mass times acceleration, centripetal acceleration, is v squared over r, v squared divided by r. So if we equate the force from the charged particle in the magnetic field, that's QVB, and the force from MA, mass times v squared over r, we equate those two, we get QVB equals mv squared over r. Let's solve for r. The r goes on one side of the equation, the QVB goes in the denominator. So now we have mv squared divided by QVB. The v takes away the v squared, so it's just we get r is equal to mv over divided by QB. So we can calculate, knowing the mass of the particle, knowing its velocity, and knowing its charge and the magnetic field, we can calculate the radius. This is the principle for mass spectrometer. The mass spectrometer, it separates the mass by the radius. It's one of the ways that it's applied. Okay, let's look over here. Now, let's say that it's not perfectly perpendicular. It's not perfectly perpendicular, but it's at an angle. So we can do the right-hand rule. You can see in this case, it's a little awkward, but the green lines are going in this direction. The positive particle is kind of going around this way, so the centripetal force is inward, and there's a helical path. If it were to be perfectly perpendicular, it would just go around without any traversing in the x direction. Now, remember we talked about the earlier when oops, I can't do that. I have to share a new share, and I have to look for not, where is it? there it is, Safari. Okay, now this is another picture of the solar wind. Remember, this one shows it also that solar wind compresses the magnetic field, actually it breaks the magnetic field, and then you get magnetic reconnection on the other side. But you can see that the solar wind, it sends particles down. See the yellow lines, they go down, and they're going in a magnetic field, and they accelerate. They go in a helical fashion. It's what we call the uh, uh, B cross V or V cross B drift. So it goes in a little helical path, and it ends up going towards the north, the northern part of the hemisphere, and it forms our aurora borealis, and on the south side it forms the aurora australis. I mean, this is a photo I got right out of Wikipedia. So if you look up Wikipedia and look up aurora, you can see the same uh, the same image. Okay, let's go back to the uh, where is there it is. Okay, so there's the helical path. Now here's that's the same on the left. That's the same image they showed us in the first slide. Here's a magnetic field region where the magnetic field is coming out of the page. So if you do your right hand rule, it's a little bit awkward for me, but you've got the magnetic field coming out of the page. Velocity is your thumb, and so the vector is down towards the blue. And this particular device, I lost it. This is what is called a penning trap. It's possible to store charged particles for extended periods. Such traps are useful, for example, in the storage of antimatter, which disintegrates completely on contact with ordinary matter. That's on page 628. But more here, what we're showing you is that the X's are magnetic fields going into the page. The dots are magnetic field coming out of the page. Okay, and I think that's just notice that it says notation. So that's what they're talking about there, how to differentiate the direction of the magnetic field from the images. And I think that's it. Yes. Okay. We'll stop there.